Okay, now we're going to look at density-dependent dynamics with discrete time model. And we're going to look specifically to really foundational models in population dynamics that are the Beaverton-Hoff model and the Ricker model. We're going to discuss briefly about stability of their equilibrium, and then we're going to run some R script to basically look how transition to deterministic chaos can occur when we use this type of models, and specific type of model. So the very first classic model here is the Beaverton-Hoff model, which was defined in 1957, a pillar widely used in fishery management and dynamics still to these days, when more sophisticated type of models are not available yet. So let's think about this model. It's about a SML per population where the adult reproduce and then they die. So we say that NT is the number of adult. We say that fertility is per capita fertility is half. So the number of eggs that are produced by the adult would be equal to F times E, and is described with ET, the number of eggs. And then sigma E represent egg survival to the juvenile stage, YT. And here is where density dependent is assumed to occur. And in this case, the assumption that Beaverton and Holt made was that the survival of eggs decreases like a hyperbolic function with the density of eggs. And thus is described by this function here, where sigma 0 is the egg survival to juvenile, a really low density of eggs, and then the term here in the denominator basically describe how quickly survival drop down when E increased. And then there is a constant survival term, sigma y, from juvenile to adults. Therefore, this is how the model is described. A number of individuals at time t plus 1 is equal to the number of juveniles in the previous generation multiplied by their survival. But how many juveniles are there? Well, it's sigma e times e, okay? So e is equal to f times n, assuming that f is discounted already for the sex ratio. This needs to be explicitly stated. And sigma e, for sigma e, we use the hyperbolic expression that we found before, okay? And so at the denominator, we're going to have rho times E is actually equal to rho times F times N, the abundance of the population at the previous time step. And so now, you can see that this is the classic functional form of a Beaverton-Holt model in which lambda is an aggregated parameter which represents, in fact, the finite growth rate of the population of really low density. So when n is really small, this term here is not really important. So the population growth in a geometric way, okay, it's a factor lambda, which is the product of per capita fecundity discounted by the sex ratio, the number of eggs that hatches and emerges juvenile, and then the fraction of juveniles that survive to the next generation to reproduce before dying. And alpha is the product of rho times the fecundity f. Now what I want to ask you is to plot this function. So try to do that. Pause the video for as much as you need, and try to draw the relationship between the recruitment, that is the population at the generation t plus 1, as a function of the stock abundance at times t, okay? And then when you have done it, try to find the equilibrium. And because this is a discrete time model, to find the equilibrium, actually, you need, as it is described here, to say basically that it's characterized by the fact that the population abundance at times t, or the generation t, is equal at times t plus 1, and you just say that this is equal to n. And then you can find what are the equilibrium or the equilibrium points of this model. So pause the video and try to do that yourself. We're going to see that in the next slide. So here it is. I'm sure you've been able to do that on your own. So this is the Beaverton function. Is a classic increasing and saturating function, where we have generation at times t versus generation at time t plus 1. Okay, so this is the increasing and saturating function. We know that the slope at the origin, where n is really small, needs to be equal to lambda, right? Because n is really small, so 1 plus something really small is basically 1, and everything is described by, the numerator. So it's lambda is the slope here, and in the long run, when n is really high, then the coefficient 1 is really making a big difference, and so in the long run, this function tends to lambda n divided by alpha n, so the 2n can cancel out, and lambda divided by alpha is the horizontal asymptote that is represented here. I draw here also the bisectrix, the 45 angle straight line, as you can see here. And this is very, it's useful because in the point, where the straight line, the bisectrix, cross the stock recruitment function that is represented here in blue, here, because, this is a 45 degrees straight line is a bisectrix here, n times t, by definition, is to be equal to n times t plus 1, right? And so, this point, which can be derived by setting n times t plus 1 equal to n times t equal to n, removing the trivial solutions, that is n equal to 0, which is also an equilibrium point, it's trivial. The other equilibrium point is actually equal to lambda minus 1 divided by alpha. And we kind of use the conventions to refer to it as K, which in this specific case is the current capacity. Okay. What we're going to look at here is cobwebbing, which is a graphical solution technique for discrete time dynamical system, which is really useful. It's moving in the outer state space model. And let's assume that we start with the population here at times 0. Okay, what is the population at times t plus 1? Well, I can draw a straight line here until it crosses the stock recruitment function, which is here. Okay, and so when we do that, basically this is the generation in time t plus 1. Okay, if I want to recompute what is the population at generation t plus 2, well, I have to basically bring this point, okay, here, and bring it down to the horizontal axis. This is nt plus 1, so I can compute nt plus 2. And a simple way of doing that is actually to draw a straight line here, an horizontal one, as you can see here, because here in this point, by definition, this is the bisectrix n at t plus 1 here on the n on the vertical axis equal to n on the horizontal axis. And so then I can just go up until I intersect the stock recruitment function again. And so if this was n at t equals 0, t equal 1, t equal 2, I repeat it, I get t equal 3, and I repeat it, and I can show that asymptotically my population tends to the current capacity. Easy peasy, you see that? So this is cobwebbing, very easy to do that, okay? So the thing we're gonna do now with the R script is to simulate these population dynamics when the dynamics can be described realistically by a Beaverton model. We assume the carrying capacity, for instance, is equal to 100, and then we basically try to see how the dynamics are both in time and in this state space plane here by using cobwebbing to look at how the dynamics change when lambda from really small, let's say lambda equal to 1.5 is then equal to 2, and then 4, and 8, and so on and so forth. One thing that you will notice, and we'll do that running, this R script, is that when we increase lambda, which I remember again is the slope of the stock recruitment functions, at the origin of this diagram, what actually happened is that if we plan things in order to keep carrying capacity constant, the curvature increases, right? And so this has happened for increasing values of lambda, okay? And by moving, because the curvature is increasing, we see that the species that are really far from the epicentrics, like the function up here, have a faster dynamic. They take less to basically approach the equilibrium. And for species with high lambda, how reproductive output at low density, recruitment is almost independent from parental stock. And in the past, I have to say, a century ago, some of the fisheries has been analyzed also under assumptions of constant recruitment, which of course is an extreme assumption. If you deplete the population and the sardine collapse here in the Monterey Bay clearly show that eventually we're going to wipe out the population. But it's true that for a population with high fecundity, this, unless the population is severely depleted to really, really low number, the capacity of bouncing back might be pretty good. Let's now move to the second model, another pillar of the population dynamics in discrete time, developed by Rickert. And here we assume that, we got again anti-adult, sex ratio discounted fertility that produce the number of eggs, and sigma is again egg survival. And in this specific case, which was a case that Rickert developed specifically with reference to salmonids and salmon population, there is these assumptions about achieving basically the carrying capacity of upstream, in a river, for which, if you have more fishing coming in, well, they use their tail to, dig up and create space to, where they lay their eggs. They're going to remove eggs that has been there already. And so there is a form of saturation. In this case, the assumption that Rickert made is that survival is actually an exponentially decreasing function with respect to the density of the adults. Okay, and so in the Beaverton-Hall model, we have a hyperbolic functions, and here we have an exponentially decreasing function. The type of model is actually everything else kind of, similar to the exercise that we did before. You see n at time t plus 1 is equal to the survival of juveniles times the number of juveniles. The number of juveniles is equal to sigma e times c, and then I can substitute basically here the function that Rickert estimated on the data to basically describe the dynamic of this population in this way. So n at time t plus 1 is equal to lambda nt times e to the powers minus beta n. And lambda, again, here is the finite growth rate of the population at low density. So what I'm going to ask you guys is to plot the Rickert stock recruitment relationship as a function of population density for increasing values of lambda. And this is an exercise, that we will do also, numerically through simulation with our R scripts. And we'll find the long-term non-trivial equilibrium, by setting again nt equal to nt plus 1 equal to n. Okay. And we will simulate again the population for lambda that is, for instance, equal to 1.25, 1.5, 2, 4, 6, 8, and I'll recommend you guys to go at least up to 20 and see how the dynamics change. You will see, and we will see together, there is an interesting aspect in a continuous time model. The non-trivial equilibrium point is, like in the logistic model, is a stable equilibrium point, is an attractor, and if there is a perturbation from the equilibrium, the population will tend to go back to that equilibrium point. In discrete time models, this is not always guaranteed, and this is interesting. So if we take a generic model here, and so nt plus 1 is equal to lambda m times nt, where lambda is the finite growth rate, which is a function of density individuals. We can find the non-trivial equilibrium as usual that we call n bar, and it's non-trivial, so we assume it's larger than 0, which is only if the small lambda, the finite growth rate, low density is above 1, of course. And then we ask if this equilibrium is stable. So we're not going to do that in this class here today in this video, but one way of doing that is to linearize the system of the equilibrium and then to find what is the dynamics of small perturbations around the equilibrium once we have linearized that. And what linearizers mean take the first derivative of lambda as a function with respect to n, and then evaluating that for n equal to n bar at the equilibrium point. And it can be proven, and it's if you're no problem of using math, it's actually pretty straightforward to find it, that if the derivative of lambda with respect to n evaluated at the non-trivial equilibrium point multiplied by the non-trivial equilibrium point is between 0 and -2, okay? And of course it needs to be negative because lambda is the decreasing function of lambda, so the derivative is negative there, and n in the other end is positive. Then we can say that if this relationship is verified, then that point is an equilibrium point, is an attractor, so asymptotically the population will tend there. There is a little bit more nuances there, which is interesting, is that if the derivative of lambda with respect to n evaluated at the non-trivial equilibrium point multiplied by the non-trivial equilibrium point is between 0 and -1, then the equilibrium point is approached without oscillations, okay? On the other hand, if the lambda over dn times n evaluated at the non-trivial equilibrium point is between -1 and -2, then it can be proved that equilibrium is approached via damped oscillation. So oscillation, so it's going to overshoot the equilibrium, then go back and overshoot and go back, but with oscillation that are basically exponentially and asymptotically damped towards the equilibrium point. Okay, and if the lambda over the n times n is smaller than -2, then that is not an equilibrium point. Okay, so and as we'll see, we're going to run the simulation and we will find what we exactly mean about that. And this is it for the moment.